My name is Dr Michelle Dickinson. I've learnt that breaking things down is the easiest way to understand them. So join me. We'll break down scientific concepts, meet some amazing scientists and inventors, and help you discover the world around you.
Hi, I'm Dr Michelle Dickinson, and I'm an engineer. I love inventing and innovating, which is just another word for making things better. I'm passionate about discovering the secrets of the scientific world around us, and have lots of amazing scientific friends who have discovered new things that help the world. Some of you may know me as the character Nanogirl, and I've borrowed her lab today to learn more about the science of light. Light is all around us, even at night, and our eyes interpret the waves that it throws out all day, every day, to give us a sense of shape and colour to, well, pretty much everything that we see. It's one of the most important scientific concepts in our natural world. And yet, what do we really know about it? Well, by the end of this episode, you are all going to be light experts, otherwise known as optics and photonics scientists. And hopefully you'll start to see things around you a little differently. Later on, we're going to do an experiment that will quite literally bend your mind. And the good news is that you can follow along with me from wherever you're watching today. All you're going to need is a pen, a sheet of paper, a half-filled glass of water, and a notebook to write down your observations. If you haven't got those things handy, go and grab them now, and then we can get started. We're also going to check in on one of my very special lab partners who's watching from home, and speaking with one of my favorite photonics experts who's going to explain how they use light to invent new technologies. Okay, let's get started. Now, you may have heard people say that something is traveling at the speed of light. But when we really think about it, what is light? Light is actually made up of waves, and the distance between the peaks of the wave are called the wavelength. Let me show you. So if this is our wave, then this distance here is the wavelength. Light travels to us from all sorts of light sources, such as light bulbs, the sun, and even at night from the stars. Whatever source it comes from, this light bounces off objects and into our eyes, which is why we can see them. On the flip side, when light can't pass through an object, a shadow is formed, and shadows can be really helpful. A quick task you can do is just stop for a moment and think of as many reasons as you can for why we might need shadows. Okay, moving back to the speed of light. Light travels faster than anything else we have discovered. It's the fastest thing humans know about, and it travels in a straight line at 300 million meters per second. That's a lot of zeros. 300 million meters per second. The straight line bit is important, but we'll come back to that later. Sound, which is also a wave, travels much slower at only 343 meters per second. You've probably noticed this difference in speed before. Like if you've ever seen a fireworks display. Usually you'll see the light from the firework explode before you hear the bang. Or what about a lightning storm? Have you noticed that you see the lightning before you hear the thunder? If you were in the location where the storm was happening, you would think you are seeing and hearing them at the same time. But that's probably not a very safe thing to do. Okay, we've covered wavelengths and speed. But what about colour? White light, like the type that comes from the sun or from a light bulb, is actually a mixture of different colours. And each of these colours has a different frequency. We'll come to that in a second. There are 7 colours of the spectrum. Let's make a list of them in order of their frequency. The lowest frequency, or fewest waves per second, is red. Then orange, yellow, green, blue, indigo, and the highest frequency, or most waves per second, is violet. You may have noticed that these are the colours of the rainbow. And when we talk about frequency, we can see how close these peaks are together. So with our wavelength, the frequency is higher for violet than it is for red. That is because rainbows appear when the white light from the sun is split by the water from the rain. Now, getting a rainbow to appear in the sky on command is not something that we can control. However, we could make a rainbow in our hand really easily by just making a soap bubble. So if I grab some soap and squeeze it into a bowl with some water, I should be able to make a bubble. Perfect. And if you look closely, you can see the rainbow colours on the surface of the bubble, as the water in the bubble breaks the white light into its spectrum of different colours. So, we've determined that light is needed for us to see things. But when it hits a physical surface, a few things can happen that changes the way that we see them. Firstly, it can reflect, which is where the light bounces off a flat, shiny surface, like a mirror, which I think we can all agree is pretty useful. Or light can scatter. This happens on rough surfaces, where the light bounces around and the roughness causes it to be scattered in lots of different directions. An easy way to see this is with a sheet of foil. Take a look. One side is shiny and it reflects, and I can see my face in it. The other side is rough and it scatters the light and I can't see my reflection. Finally, light can also refract. This happens when light passes through a different substance, like from air to water. As it passes through, the light might change speed or direction before it gets to our eyes. There are lots of ways to see refraction in practice, so let's try a refraction experiment. I'll just dial in our special contributor. Hey Hudson, tell me a bit about you. What do you enjoy doing?
I really enjoy cars and the whole mechanics about just cars in general, really.
Well, it sounds like engineering might be in your future. Have you thought about that?
Yeah, when I'm older, I feel like I want to do maybe car mechanics or engineering.
That's awesome. Well, you've come to the right place as a fellow engineer. I think that's a great career. I might be a little bit biased. And we're going to start your engineering career today with a science experiment to help you with some physics. Is that okay?
Yeah, that's great.
I have a question. Have you ever heard the expression, "It's just a trick of the light," before?
I think I've heard it, but I don't know what it means.
Well, today we're going to do an experiment that's going to use the light, I think, to trick you. We're going to give it a go. So just checking that you've got all the ingredients in front of you. Do you have half a glass of water, a piece of paper, and a pen or a pencil?
Yeah.
Okay, so the first experiment that we're going to do is you're going to pick up your pen or pencil and just hold it in front of you. Okay, so take a look at it and tell me, is it the same width from top to bottom?
Yes.
And is it straight or is it bent?
It's straight.
Perfect. Okay. Now what we're going to do, now you know those 2 facts about your pen, we're going to put it in the water. So put the glass of water in front of you, and then you're going to dunk your pen in. But before you do that, I want you to predict or come up with a hypothesis as to what happens next. So what do you think is going to happen to the pen and how it looks when you put it into the water?
I think it'll just stay the same.
Just stay the same. Okay, so here we go. Drop it in. And take a look at it. Does it look the same in the water versus out of the water?
No, it looks more big.
It looks bigger, and does it look a little bit bent, like there's a bit of a kink in your pen?
Yeah, definitely.
Okay, we're gonna double check that it hasn't magically grown because it's in the water. Just pull it out for me a second and double check that your pen is straight.
Yeah, it's straight.
Okay, and put it back in and check that it appears to be bent now in the water.
Yeah. Whoa.
It's cool. Okay, so that is a trick of the light. That is refraction. We're going to do another experiment to show you that. So take your pen out of the water. Here's what I want you to do. I just want you to tear a bit of paper that's about the width of your glass.
Oh, not doing a great job here.
That's okay. Okay, Hudson, what I need you to do is write the letters W-O-N on the bottom of your paper in small letters, not capitals.
Okay. W-O-N. Okay.
Fabulous. Right, now put your glass of water in front of you.
Okay.
And you're going to put your head down so that you can see at eye level the water. Great. Now grab your piece of paper and put the paper behind the glass of water. Now just double check that it says W-O-N on it.
Yep, definitely.
Okay. And I want you to put it behind, again, about maybe a hand length behind your glass of water, and then read the letters through the water.
Wow.
What does it say?
It says now.
It says now, but hold it up. It definitely says 1 on your paper, yeah?
Yeah.
But when you look through the water, does it say now?
Yeah, that's so cool.
And so that is a trick of the light. That is refraction. What's happening is the light is bouncing differently through the air compared to how it goes through the water. So when it hits the water, it changes direction, which means that the way that we see things through the air is different to how we see them when they go through water, even though they're both transparent. And so you just learned how to make a secret code, basically, by using water. So it means you can put secret messages everywhere, and as long as your friends know to read it through the water, then you can put messages around your house and your parents won't see anything.
Would this work on other things as well?
Probably as long as they're waterproof, but the great thing to do is test it first. So maybe if you've got a ruler or something waterproof, put it in and see if the same thing happens, because that's all about how we learn science. We experiment, we try some things, and then we find out. Hey Hudson, this has been great. Has that helped you understand refraction?
Yes, actually.
Thank you so much for helping me with our science experiments today.
Thank you for having me.
Okay, after any experiment, we need to write down our observations. These help us to understand our results and make interesting predictions for our next experiments. So, my observations today. Well, what did we see? I saw that the straight pencil actually looked bent and fatter through the water. I also saw that the word 1 looked like now through the water. Both of these are caused by refraction, changing the speed and the direction of the light, which makes our eyes and our brain perceive it as different. Now that we have written down all of our observations, we need to reflect on our data. Do we think that this is always what happens with refraction? Or do we need to run more experiments? What if we tried with a fluid that had a different viscosity or runniness, like honey? How about a larger item than a pencil, like a ruler? You can list your own, but some of the things that I'm thinking about are: do you think the results would be the same if we changed the fluid or solid object? Why not try dipping some other waterproof items in your glass and observe what happens? Maybe a ruler. Where do you think we could use refraction to help us in real life? Have a think and maybe write down some ideas. Refraction is just one of the many concepts when it comes to the science of light. And there are so many amazing scientists and engineers working on light to invent new things and innovate to make current technologies better every single day. Why don't we meet one of them now? Associate Professor Jevon Longdell is an optics and photonics scientist working in quantum mechanics. He's working on ways to make it much harder for people to hack into our computers or steal our data. All of his projects are powered by light. Hey Jevon, how are you?
I'm great. How are you?
Great. Thank you so much for joining me. Can you just introduce yourself to everybody?
So my name's Jevon Longdell. I'm lecturer and a researcher at the University of Otago and at the Dodd Walls Centre, which is a multi-university New Zealand research institute.
Amazing. Look, today we've been talking about light. We've done an experiment using refraction and we've played around with the bending of light. And your job is in light, yes?
Yep.
And so where did that start? From a kid, did you want to be a scientist who was specializing in light?
As a kid, I don't think I wanted to specialize in light, but I was very, very interested in science from an early age. I guess when I was, like in primary school, whenever I asked my parents a question that they didn't really either know the answer to or wanted to answer to, they'd say, well, you'll do science in school one day and you'll learn about it then. And so when I got to high school and did kind of science as a more serious subject, I was really primed to go, and I guess I've been in love with it since then.
So you work at the Dodd Walls Centre for Quantum and Photonic Technologies. Tell me what people do there.
It encompasses people doing research in two what turn out to be quite related areas. One is quantum technologies, and then there's light. We study how light behaves itself and all sorts of different applications for light. For example, the reason that we can all talk to each other on Zoom is because we're communicating with light, right? I mean, I'm sort of old enough to have used the internet before fiber optics were ubiquitous, and you couldn't use photographs, right? You could send short text emails, right? And it was cool that they got down to your friends studying at Otago. I was at Waikato, almost instantaneously. I mean, that was really neat, right? But you couldn't send them a photograph because it just used too much data. And the thing that enabled people to send photographs and then videos all over the internet was communication by light.
And so fiber optics uses light, is that what you're saying?
Yeah. It actually uses light it uses infrared light. So you can't actually see the light because it's just the wavelength is just a bit too long to be sensitive to your eyes, but it's light.
So today we've learned about the colours of the rainbow and the spectrum, a little bit about what wavelength means and frequency. So infrared light is on that frequency, but high or low?
Lower frequency, longer wavelengths. If you look at a rainbow, there's the red bit, and then if you look above the red bit, then your eyes can't see it, but that's where the infrared light is coming from.
Perfect. So tell us about what you do in your research. Do you use rainbow light?
I generally use laser light, right, which is like really, really purified light. Like the wavelength is a very, very, very particular wavelength, and I use this very, very pure laser light to manipulate impurity atoms in cold crystals, right? So you have our crystals look just like a bit of glass, right? And they have impurities in there which we sort of manipulate with the light pulses. And in doing so, we're working towards doing useful stuff for making quantum computers.
And so quantum computing, we've heard this before, it's probably the next phase of computers. Why are we excited about quantum computing?
I think it's wrong to think of them as just like being really fast computers, right? The thing about quantum computers is that they will enable us to solve problems which are completely infeasible, right? So for some problems, they'll just blow the pants off current computers.
We are trying to share knowledge about the science of light, and you obviously are a light specialist. So if there was one science of light fact that you think that everybody should know, what would it be?
One thing that I find continually just mind-blowing is that we can make lasers that have got reasonably high average power, right? But they've got really, really, really short pulses, and so short that all this energy is so concentrated, in that we can put more power through the width of a human hair than is used by humanity. So all of the world's electricity, even when we're all working hard, all of that energy, all that power, you can concentrate down into something the size of a human hair, which is neat, and it enables, obviously anything that you put in its way just gets completely obliterated, and you can do all sorts of cool things like that. So that's a fun fact about light.
That's pretty fun, and I think that might motivate some people to want to study physics and therefore go on to study lasers with their obliteration properties. Hey Jevon, thank you so much for joining us today.
Thank you for having me.
Okay, So lasers, like Jevon was talking about, are truly mind-blowing. Did you know that because lasers are made up of such narrow beams, they can travel very long distances? So far, in fact, that lasers have even been used to measure the distance between the moon and the Earth. Scientists did this by measuring the amount of time it takes for a laser beam to travel to the moon and back, so astronomers can tell exactly how far away it is. Technology using light is all around us, and now you know about it, I bet you will start to see laser technology everywhere. You might have noticed them at the supermarket, being used to scan barcodes on your shopping, or noted that your printer was actually called a laser printer because it uses lasers to help ink print onto the paper. We use lasers as high-precision tools across a lot of different industries. And we do that because they can cut through diamonds and thick metal, as well as accurately in medical surgeries. You might know somebody who has had surgery on their eyes so that they don't need to wear glasses anymore. This will have been done using lasers too. The future of light looks pretty exciting. But don't forget to explore how light affects you every single day. Think about how photographs work, or movies. Why does light wake you up or send you to sleep? How do you think sunglasses work? There's so much to discover, just keep asking questions and testing your theories by experimenting. Teachers and parents, if you would like to keep teaching the science of light, why don't you visit Nanogirl's lab and click on Teachers? We have lots of downloadable content and links to help you continue on your science of light journey. Since a star's light takes so long to reach us, how do we know if the star is still there? If both sound and light are waves, why can we hear sound around a corner but not see what is making the sound? Why do some objects let light travel through them while others don't? Why is the sky blue?